Okay guys, let's go ahead and talk about this warm-up question. Hopefully you took a moment to look at it yourself and try to answer it on your own. If not, then look at it with me now, and it should be something that you copy down into your notes for today. It says, which could show the velocity time graph for an object in free fall that was dropped from rest? So first things first, these are velocity time graphs. It says it in the question, but it's also labeled that way on the axes. Each of them says VT. And so first thing you need to think about is how you need to represent motion on a VT graph. So in this case, for something that has been dropped from rest, what should my initial velocity be? Zero, because it was dropped from rest. So my initial velocity needs to be 0. On a VT graph, how do I show that my velocity is 0, my initial velocity? It needs to start at the origin. Okay, if these were position time graphs, they're not, but let's pretend for a second that these were XT graphs, then you would be looking for a graph that starts out horizontal, okay, because that would mean it was at rest. But we don't have a we don't have an XT graph. These are velocity time graphs. So if I want to show my initial velocity is 0, then I need my graph to start at the origin, because that means the velocity is 0 at time 0. There are only 2 graphs that start at the origin, C and D. So from there, what should my acceleration be for an object that has been dropped from rest? If it's in free fall, what's the acceleration? Negative 9.8. I heard a couple people say it. Remember that number. Okay, negative 9.8 meters per second squared. Does that number change? No. So you also need to remember that the slope of your VT graph represents your acceleration. And if my acceleration is constant, then my slope needs to be constant, which means it needs to be a straight line. So of the 2 we have remaining, that means it has to be answer choice C. That would represent an object dropped from rest. It's accelerating at a constant rate. Specifically, there are no numbers on this, but it would be at negative 9.8 meters per second squared. Okay, so these, you need to be able to interpret graphs, and that's something you're going to be doing today in class once we get to the card sort. So it's important that we kind of review it real quick now as well. Just to add, if these had been position time graphs, if they had been XT graphs, then either graph A or graph D could have shown something dropped from rest, because they both start out horizontal and they both show something that's moving downward and increasing in speed. They just are dropped from different heights. Okay, but those could be, either of those could actually represent it if they were XT. They're not, but if they were. VT, only C. All right, so we're going to do some recap, some notes on free fall and graphing real quick, and then you have your card sort with the quiz, and that will be homework if you don't finish it in class. I would strongly encourage you to copy down this example problem. We have talked about things being thrown up in the air, but we have not calculated one of them together. And there was one, I think, on your assignment yesterday. So some of you may have had some trouble with it, or maybe you figured it out, because like I said, we did talk through it. We just didn't do one together, so I wanted to do one together now. And if you needed to go back and look at that question again after we go over this, you might be able to go in, you can go in and answer it again. All right, it says a ball is thrown upward at 3.4 meters per second from the ground. What will be the maximum height that it reaches? So again, anytime you're analyzing a calculation problem like this one, we're going to start by labeling our givens. The only number given to us in the question is the initial velocity that it's thrown with, and that's going to be an upward or positive 3.4 meters per second. That's it. That's the only thing in the question, but it is not the only thing that we know. We know that this is a ball that has been thrown and thus is in free fall. Okay, you can be in free fall while moving up or down. It doesn't matter. If the only force acting on it is gravity, which it is as soon as it leaves your hand, then it's in free fall. So we know the acceleration. It's the same one you mentioned in the warm-up a second ago, negative 9.8 meters per second squared. Okay, and that seems like the only things that we know, but it's not. Again, I talked about an object being thrown upward in class when we did notes. What else do I know about the motion of this object? The final velocity, okay, at what point? At the top. Guys, I know the velocity at the top. If I throw something upward and it rises to some maximum height, how fast is it moving once it gets there? 0. Because it has to stop moving upward so that it can start falling back down. So these objects will stop momentarily. They don't sit up there like a Wile E. Coyote cartoon, but they do go up and then turn around and fall back down. And for that instant, it is 0 at the maximum height. And so my final velocity at max height is 0. Now, I do also know what my final velocity would be at the end of the trajectory, assuming that it lands at the same height it was launched from, because it's all symmetric. But I don't really care about the end point, because the question doesn't ask about the end point. The question asks, what height does it reach? So we really want to focus on that top point. But just to mention it, in case you're not aware, my velocity at the end, if it lands at the same height that it was launched from, the end velocity is equal in magnitude to the beginning velocity. So since it was launched at 3.4 up, it will land at 3.4 down. I don't need that information for this question, but it could be something that you use for future questions if you're solving for something and you want like the whole trajectory. For this one, I'm using my final as the max height because that's what the question's asking for. Okay, so I'm going to focus just on the first half of my trajectory. I have VI, I have A, I have VF. That is enough for me to find height, which is displacement. How far off the ground is it? That's your height. So with that, you're going to look at your equations. Which of these equations should I use to solve for delta x from the information that I have? A, B, C, or D? Take a look if you're not sure. I heard a couple people whisper it. Which one? Okay, so I heard A and I heard B. Those are actually the only two equations you can use. However, if you use equation A, you can't solve for delta x. You can only solve for t, which you could do and then find delta x if you want. If you use equation B, you can solve for delta x in one step. I told you guys there's more than one way to do this, but B is going to be the fastest way if you want to do it in a single step. So that's what I'm going to do. We're going to use equation B, VF squared equals VI squared plus 2 times A times delta x, and we're going to substitute into that equation. It looks like this. 0 squared equals 3.4 squared plus 2 times negative 9.8 times delta x. So now you've got a math problem. 0 squared is 0. 3.4 squared is 11.56. Okay, and 2 times negative 9.8 is negative 19.6. I've already actually rearranged it a little bit because when I squared that 3.4, I went ahead and subtracted it to the other side. So 0 minus 11.56 is negative 11.56, and that's equal to negative 19.6 times delta x. Okay, from here, to get delta x by itself, we need to divide because it's currently being multiplied by that negative 19.6. So we're going to divide both sides by negative 19.6, and that gives us delta x equals positive 0.59 meters. That represents the maximum height that this ball would reach. Yes?
This might be like a stupid question, and I understand that like acceleration for like free flowing, it's always going to be like negative 9.8 even if it's going up or down.
Right.
But, like, how come even when it's going up, it's going to have the same acceleration as it would be going down?
If you didn't have a negative acceleration while the ball was rising, then the ball would never come back down. So that negative acceleration is what causes it to slow down.
Okay.
Yes, it's always pulling downward. Okay, any other questions? All right. So let's do a follow-up question, because we could also solve this. How long is the ball in the air? Okay, by the way, I've added delta x to my information that I know, because I now know what it is. Okay, and so now we can solve for time. Okay, now I do want to caution you to be careful here, because if I solve for time with the information that I have labeled here, I'm only going to be finding the time it takes to get to the top, because that's my velocity at the top. And that's my displacement at the top. So if you use these numbers, you're only going to get the time it takes to go up. Keep that in mind, because when you get it at the end, we want the whole time. And it's symmetric, so we're just going to double it. You'll see that in a minute. All right, so I'm looking for time. Again, here are my equations. Now, this is a little bit of a different scenario because I know every single value that's on that screen now. I know VI, I know A, I know VF, and I know delta X. I can find time with any equation that has T in it, which means I could use A or C or D. Now, I will caution you and suggest that you not use equation C. If you try it, you'll see why. But if you try to solve for time with equation C, you will have to use the quadratic formula. I would recommend against that. You could if you want. Okay, I would use equation A or D, and personally I think A is easier, so that's what I'm going to use. So equation A looks like this. VF equals VI plus A times T. If I substitute in the numbers that I know, I have VF is 0, I have VI is 3.1, I have negative 9.8 for A, and I'm looking for T. From here, you need to do the math. This just becomes an algebra problem. Again, just as a reminder, algebraically speaking, you cannot add 3.4 and negative 9.8 together. They are not like terms. Okay, instead, you need to move one of them to the other side of the equation by subtraction. So we're going to move 3.4 to the other side, giving us negative 3.4 equals negative 9.8 times T. And then to get T by itself, we're going to divide because it's being multiplied. When I divide both sides by negative 9.8, I get a time of 0.347 seconds. But again, that is not the total air time. That is just the time it takes to get to the top. So once you get this number, you're going to have to double it. Okay, so 0.347 times 2, 0.694 seconds. That would be the total time that the ball is in the air. Any questions about this one? No? Okay. So again, you should be able to do calculations for objects thrown upward as well as things dropped from rest or thrown downward. All right, so let's go to graphs because that's where we're going to be going in a minute, card sort. So what do the graphs look like for this object that's been thrown upward? Well, my XT graph needs to show an object that starts out moving in the positive direction, but then turns around and moves in the negative direction. And it needs to slow down as it turns around, so it looks something like this. In fact, it looks like the trajectory of the ball itself. Okay, so my XT graph looks like that. My VT graph needs to show an object that starts out with a velocity of positive 3.4. It needs to cross the x-axis because it needs to start to fall back down. And at the x-axis, when it does that, that's going to be my max height because the velocity is 0. It's going to look like this. It's going to start up here at 3.4. At this point, we're at max height, and then it's going to go down to negative 3.4 before it hits the ground. And then AT. Again, for your AT, use your VT graph. The slope of the velocity time graph is your acceleration. The slope of that VT graph is negative. And I know what it is. It's not, there's no numbers here, but specifically that graph has a slope of negative 9.8 because it's free fall. Okay? And so my acceleration needs to be in the negative region. You don't have to know what the number is to draw this. You just need to look at the slope and say that's a negative slope. I have negative acceleration. All right, so again, if you can draw the graphs, you can match them. I promise. Drawing them is harder than matching them, I think. All right, let's try to draw some more just for some practice before we get to the card sort. So here is a VT graph. I would like you to take a moment on your paper and even converse with your neighbor if you want to and see if you can draw what the XT and AT graphs would look like that show the same motion that's represented in this VT graph. I'm going to start a 33-second timer so that you guys have some time to sketch out your two graphs. Again, if you're not sure, turn and talk to your neighbor, and then we'll go over it when this timer goes off. Okay, hopefully you were able to figure that out, but if you weren't, or even if you were, I'm going to give you a tip right now. Okay, here's a tip to help you do this. It'll also help you with the card sort. You might want to write it down. As you look at any of these graphs, ask yourself these two questions. The first question is, which direction is this object going? Okay, which direction is it going? Is this going forward or backward? Backward. Ask yourself that first. Okay, the second question you need to ask yourself, is this object speeding up, slowing down, or moving at a constant speed? This one is a constant speed. If you ask yourself those two questions, it will help you with your VT and your XT graphs, okay, both of them. Okay, so we're looking for something that is moving backwards with a constant speed. So how do I show that on an XT graph? Well, backwards on an XT graph means that I need a negative slope. Okay, so it needs to have a negative slope. And the constant speed part means that the slope needs to be the same the whole time, because your slope is your speed. It needs to be a straight line. Don't draw a curve. Draw something that looks like this. Now, it could have a different y-intercept, okay, but it needs to have that shape. Okay, so that would be an object that is moving backwards at a constant speed. All right, AT graph. Different question for the AT graph. All you need to ask yourself for the AT graph is, what is the slope of the VT graph? So looking at that VT graph, is the slope positive, negative, or zero? Negative. The slope. Is that a positive slope, a negative slope, or zero slope? Zero. That has no slope. It's a horizontal line. So zero slope means zero acceleration. Yes, it's a negative velocity, but it's a zero slope. So check the slope. All right, let's try another one. This time I'm going to give you an XT graph. Same thing. Ask yourself those two questions. You can turn and talk to your neighbor if you want to work with somebody on it. I'll give you 33 seconds again. So turn and talk to your neighbor. See if you can draw what the VT and AT graphs would look like that match this, and then we'll go over it in 30 seconds.
This is the VT.
All right, hopefully that one went a little smoother if you had trouble with the first one. Again, two questions. Which way is this object going, forward or backward? Forward. Is this object speeding up, slowing down, or moving at a constant speed? Speeding up. I know that because the slope is getting steeper. Okay, so it's not a constant slope this time. My slope gets steeper, it's speeding up. So I need to show on my VT graph an object that is moving forward and speeding up. Okay, on a VT graph, if you want to show forward motion, you need to be above the x-axis where the positive velocities are. And if you want to show that the velocity is getting faster, your graph needs to move away from zero. Okay, so it would look something like this. Again, this one is showing that it didn't start from rest, which if I look at my XT, it does have a slope here. It doesn't look horizontal at the beginning, so I didn't start at the origin. Although you might have been able to get away with it in the card sort. I don't know if it's that picky. But I have something that starts with a positive velocity, but then that positive velocity gets faster and faster. And again, we're only going to draw straight lines on our VT graphs, just as a reminder. Curves only show up on XT. All right, for my AT, again, all I have to do is look at the slope of my VT. Is the slope there positive, negative, or zero? Positive. So my AT is positive acceleration. Okay, again, if you can draw them, you can match them. Yes?
Does it matter where, like, for the acceleration time graph, does it, like, since the slope is, like, near, like, the bottom, can the line for the acceleration...
Are you talking about the y-intercept?
Yeah.
Yeah, the y-intercept would not have any effect whatsoever on how you draw your AT graph.
It could be anywhere in the positive.
Right, it could be, depends on what the slope is, but yeah, it needs to be positive somewhere depending on what the slope is. Since I don't have numbers, I'm just looking at shapes here. All right, how about this one? You should also be able to draw your graphs from a description or match them to a description. So let's try this description. It says draw the graphs for an object moving forward from the reference point and slowing down. Since you have to draw 3, I'll give you a little bit more time. Let's go ahead and do 36 seconds. Again, if you're not sure, turn and talk to your neighbor, but see if you can sketch these 3 graphs, and then when the timer goes off, we'll go over it. Again, ask your neighbor if you're stuck.
You're obsessed.
Ow, you didn't even know what I'm writing. No?
Just sign. So what's the VT graph for this one? So it looks
You don't even know what I'm writing.
All right, hopefully that was enough time. If not, that's okay. We're just going to move right on. Again, I've already answered the 2 questions for you. It says forward and slowing down, okay? And it tells you where to start, the reference point. The reference point, by the way, only going to be helpful on my XT graph. That's the only graph that shows me where I start. Okay, so on my XT graph, I'm going to start at the origin, position of 0. That's your reference point. That's what it's referring to. Okay, and we're going to show something moving forward. That means a positive slope. And it needs to slow down. So that slope needs to get flatter or less steep. So it needs to look something like that. Again, that's the shape. It does need to start at the origin because it says from the reference point. So this time it matters since it's specified. On my VT graph, again, forward motion means I'm in the positive region above the x-axis. And slowing down means that I need to go towards 0. It needs to approach 0. Because if you get to 0, you have stopped. So this graph shows something that's moving forward and slowing down. I can't tell where it started. So that phrase from the reference point doesn't show up in my VT graph at all. It only shows up in my XT. Last one is AT. Again, for your acceleration time graph, look at the slope of your VT graph. Is that slope positive, negative, or 0? Negative. So you need to have a negative acceleration. Okay, if you can draw them, you should be able to match them, and that's what you're doing right now. Please make your way to My Open Math because you have an assignment 204 acceleration card sort. It's going to take you to Amplify again. That's the former Desmos classroom. It's pretty much the same as the last card sort with one major difference. You're still matching them in sets of 3. However, y'all might want to listen because otherwise you're going to be confused. There are 2 cards missing, and it's done intentionally. Okay, so when you're matching them, you're going to have sets of 3 and then 2 sets of 2 because 2 sets are missing one of the cards. Okay, so you're going to notice if you count them that you're going to have different numbers of some of the cards. So anyway, that is intentional. It's going to be asked about on the quiz. When you take the quiz, it's going to say, hey, you were missing a card. Which one of these was missing its VT graph or whatever? So you're going to answer it on the quiz. The grade, guys, the grade for this is the quiz grade. But you need to do the card sort first, especially because it's missing cards that you don't know what they are until you do it. You need to do the card sort first so that you can do the quiz and answer the questions right. As you do the card sort, if you want me to check it, I can pull it up on the screen and you can see which ones you have right, which ones you have wrong. Okay, the card sort quiz is due by 11:59 p.m. tonight, so please make sure you get the card sort done in class today because that's going to make your life a lot easier. You can even possibly finish the quiz too, but at the very least get the card sort done. You can do the quiz at home as long as you have done the card sort. Okay, if you have questions as you're working, let me know, but I'm going to encourage you to work with the people you're sitting with. You have the same cards that they do, and see if you guys can get them matched up.
I only